So I'm David Bader. I chair a school at Georgia Tech called the School of Computational Science and Engineering. And I'm really pleased that Neo4j has allowed me to talk to you today at Graph Connect 2018 about predictive analysis from massive knowledge graphs and some of the work that we're doing with Neo4j. This is a fantastic meeting. I love networking, getting to know many of you as we build out our own graphs and as they come together. So thank you again for coming and listening to me. So my school is absolutely fantastic. In fact, we're building a new building that's almost complete, that's in the lower right-hand corner of the slide, called CODA, which is really a facility dedicated in the Southeast US to data sciences and engineering. And my school will form the core of that building. So it's quite an interesting time. And we have lots of companies that we collaborate with. Now, my research area going on at this point, many years, in fact, decades, has been trying to solve real-world grand challenge problems that involve data. And in the process, we have worked on some of the most challenging and largest and most demanding graph analytic problems, ranging from healthcare, for instance, looking at health informatics, understanding patient outcomes, looking at the spread of pandemics and disease, all the way through massive social networks on how we connect with each other, transportation systems, how to evacuate within a storm, for instance, Hurricane Florence, and getting many people out of the way of harm, all the way through business intelligence, looking at systems biology and how genes and the proteome affect life, the electric power grid that's important for food production, energy, transportation, communications, and all the way up to modeling and simulation of full economic, social, political simulations of, say, nations. Now, this is a challenging application space. There's lots of real-world problems that affect the human condition that we're trying to engage with. And often, we have data sets that overwhelm a single computer. And we need to have answers not an hour or a week from today, not even 5 minutes from now, but often in milliseconds, or we'd like to have the answers even before we thought of what those questions are. So some sample types of queries that we look at are try to understand communities within populations and individuals that may be core in some community, but over time may move to be core in another community. Or as new information arrives, how do those communities change over time? For instance, am I losing customers? Why are they leaving, et cetera? We also work on a lot of applications where we're looking to identify new patterns that we haven't seen before. For instance, in cybersecurity, we deal with threats and giving attribution to different types of attacks, some of which we may not have seen previously. So all of this requires predicting and influencing change in real time at scale. So that's the hallmark of the research that we've been doing. And through my talk, I often describe things in terms of a social network where it's easy to talk about people and their relationships, but in fact know that we use this metaphor to apply to a variety of problems related from network traffic to business intelligence to DNA and on. So graphs are really pervasive in my line of work in academic research, in science, physics, chemistry, astrophysics. We see graphs all over the place. And what my job as a graph analyst is to do is to take these real-world problems and look at the graph abstraction and help build out algorithms and tools that help solve these problems. For instance, on the left, I have an example from detecting quasars in astrophysics, where we may have two digital images of the sky over time, and we're looking for changes that could be a quasar in order to detect it very fast and move a telescope within minutes to try to catch that celestial event. So here we may be looking at temporal variations in the image and a graph problem like graph clustering or matching between those images and those bodies. In the middle, I have an example of a problem in bioinformatics where we're trying to identify drug target proteins, and we have, say, a protein interaction network where we're looking for maybe proteins that are central using between centrality or other centrality network algorithms, or clustering of those proteins. And finally, on the right-hand side, social informatics, where we may be looking at shortest paths between individuals in a social network, flows of information through an organization, et cetera. Now, today, a lot of work is done on forensic analysis of these data sets, but as we go forward, we're going to be tapping into these data streams where we're trying to make decisions on the fly as we go. And that's really in the face of these challenges of different data sizes as our data gets larger and larger, especially for these graphs, heterogeneity in the data, uncertainty, and different qualities of the data that we have. And at the end of the day, what we would like to do is make better decisions that really drive our business or organization. And I think these data analytics are really going to define the next set of companies that are able to monetize and have better efficiencies within their organizations and how they deal with others. And this area of graphs is really going to change the world. So some of the areas that I'm going to talk about today are using graphs for areas of intelligence and surveillance. These are just two public images. The top represents the hijackers on September 11th, and it was claimed that if you could have done graph analytics at that time, 15, 20 years ago, that you would have been able to detect the hijackers, the ringleaders, the different cells on the planes using algorithms like centrality. On the bottom is another example of a type of graph analytic, and there is observed information and a pattern that you know is suspect. Two individuals who live together, they're observing a workplace, one rents a truck, the other buys fertilizer, they may be, up to no good, and what you'd like to do is be able to find different versions of that type of pattern within a large data set. And this is called subgraph isomorphism, or more commonly known as graph matching or motif finding. So these are hard and challenging algorithmic problems, especially in the face of growing and massive data sets. Our group is one of the first, for instance, in fact, we are the first, to take a full set of tweets that were public and put into the Library of Congress in the US. Back a decade ago, we took tweets from around September and October 2009, and we put them into a supercomputer over here called a Cray machine. Some of you may recognize the name Cray. And we work with Pacific Northwest National Lab, and this was terabytes of information. And what we were looking at was, actually taking a step back to 10 years ago, is Twitter good for anything? That was really, can we get any good out of tweets? Now, I've since learned you could become president. So about 2 years ago, I started tweeting, and my plan is in about 6 months to take over the world. So if you want to follow me on Twitter, that's great. But at this time, we weren't sure. Everyone was wondering, how do you get value out of tweets? So we took two events in that period. And let me just tell you about one of them. On the left, you see H1N1. If you can recall back about 2009, there was this scare that this new variant of virus, H1N1, was going to have double-digit mortality around the world. This was scary. People didn't know what to do. There was a panic that ensued that we have to be very careful with air travel and a global world that we live in, that we're going to see massive deaths coming out of this. So we decided to take all the tweets and use the followers and followees and some of the keywords of the content and build a graph. And from that graph, we ran between a centrality on that graph as an ad hoc measure to see what was the most influential handles that we could find on Twitter related to this event. And so I have about, I have about 15 of them up here on this slide, and some of them are obvious. This is where people were getting their information from about the virus. And you see the CDC is #1. That's the US Centers for Disease Control and Prevention, where you would expect many people to turn. And you see #4 is flu.gov, and a couple of these are the CDC later in the list. You also see commercial media like CNN, New York Times, Time Magazine, and you'd expect those also to be very influential as to how people are learning about it. But the power of graphs is more than that. On a breaking event, how do you know who to listen to? How do you know who is the source of information and the most influential? And it turned out that one of the top ones on this list, you'll see it #3, official PACs. Now, I often talk to academics and I say, does anyone recognize official PACs? And nobody answers. Maybe you'll do better. Has anyone heard of official PACs? I mean, certainly if there was a disease outbreak, none of you would ever turn to it. It turns out that this was the penny exchange, penny arcade. These were primarily adolescent male game players who were in Seattle at a meeting of this conference where they're playing games. And they were one of the first groups in the country, in the US, to contract H1N1. And they started tweeting with each other, like, hey, do you have H1N1? Yeah, it's confirmed. Yeah, me too. Hey, buddy, do you have it? Yeah, sure. What are the symptoms? Well, I won't repeat it here. And they start talking about that. And hey, did you die? No, not dead yet. Did you? No? Yeah, you're not dead? Okay, cool. And so that was one of the primary sources of understanding how deadly H1N1 was, what the symptoms were, and you never would have thought about tuning into that in advance, like tuning your radio dial to a source for news. That's the power of graphs. How, during events, do you know what to listen to? So I love that story. I was giving a talk a number of years ago in India, and a student must have been the biggest fan of the Backstreet Boys. How many of you have heard of the Backstreet Boys? So I got asked, why are the Backstreet Boys up there? And so I scratched my head a little bit, and I said, well, I have no idea. I'm gonna have to go research that. So we went back to the data, we did some analysis, and this is the case where graphs are very good at giving you information, but as Hillary mentioned in her keynote talk this morning, you always have to look at the models and the data and understand there's always anomalies. And it turned out the Backstreet Boys had released an album, and so fans would be tweeting about the new album and H1N1 together. And so this is just where it's some crossover, and it's just an interesting phenomena. So always when you have data in these real-world problems, you get some information from graphs, but you always have to go and check what you have and do a reality check always when you're working with these data problems. We have also worked, as I mentioned, on finding resiliency in the US power grid. So this is kind of a cartoon graphic of graphs of the power grid. In the US, we primarily have an eastern power grid and a western power grid. And we work with Pacific Northwest National Labs in partnership to look at the resiliency of the power grid. That's represented as a graph problem. And we know that single failures on our grid can lead to massive blackouts of whole regions. On the right is a problem that we worked on looking at the human proteome, and we ran between-us centrality on the proteome to find proteins that weren't the most interactive. They were like the needle in the haystack, but they were the most connected in some sense in a centrality measure. And it turned out one of the proteins that we identified that had the highest centrality had been implicated in breast cancer. So when we think about graphs, we really have to look at other places where it may give insights that you wouldn't ordinarily see and use those graphs as a way to help solve real-world problems. So my lab has been doing this for, gosh, probably 20, 25 years, and it's called STING. The Georgia Tech mascot is over there. It's this yellow jacket, and STING stands for Spatio-Temporal Interaction Networks and Graphs. So we work on real-world problems that can be modeled by graphs that change over time, often where the vertices and edges have spatio-temporal locations, properties, timestamps, and other features. For instance, we have worked on a DARPA program that was aimed at solving problems like, if you recall a number of years ago, Major Nidal Hassan was an Army psychologist and also a Fort Hood shooter. So he had a clearance. He was part of what you'd think of as those trying to look out for the mental health of others. And seemingly one day he came in and he shot and killed a number of people. So how in a system do you deal with insider threats where you have an individual who may change over time and do nothing wrong before some egregious event happens? Those are the types of problems that we try to look at. And I mentioned a few of the other examples up here. These problems are hard. We often have information that becomes large, and we have to build new algorithms and even new computers to be able to solve these problems in real time. So we've also helped engineer new computer architectures and partnered with companies like Intel, Qualcomm, NVIDIA, IBM, and others, Cray, to build new computers that often those components you then see as you're using your smartphones in a number of years, those technologies trickle down. And I hope someday that we can run all of our Neo4j applications just on our smartphones, or maybe in some device that's embedded inside of us by that point. So Stinger was really built for a solution when the analysts that I work with who may use Neo4j would get to a point where they had trillions of entities in their graph, or they needed response times in milliseconds for graphs where you're connecting to a fire hose of information. And so we've worked on early algorithms in research on looking at properties that you may run in Neo4j today, for instance, connected components, shortest paths, community detection, but how do you track those changes as your graph is changing underneath you in real time? And how do you detect, flag, and report changes that are significant to your customers and users? Now, on the talk today, I want to jump into some depth on a problem that we're doing for Homeland Security. And this is really a current work in progress, where we have analysts that are taking natural language reports in multiple pages with references, footnotes, and figures, and they're being charged with trying to, for instance, protect special events that happen. For instance, just down, or outside, I should say, in New York City, we have the Macy's Day Parade, or the Super Bowl that happens around the country. These types of events we would like to go to and be safe at, and there's some very important work that's being done to try to make sure that the local law enforcement is aware of what's happening and that you remain safe as you go to these events. So analysts manually discover and rediscover relationships among the reports and the open data sets that they have access to. And I should say everything is typically kept open so that it can be shared with local law enforcement, with the public, and be used. So this is an open type of problem. And graphs are a natural and important structure for connecting this knowledge together. So our approach was to help Homeland Security build a knowledge graph. We've ingested prior reporting, events, newspaper articles, different types of attacks, known bad actors, and try to hook this together in a graph working with DHS, FBI in New York, NYPD, and others. And we built the graph on top of spreadsheets, raw data sets, handwritten notes, reports, et cetera, and then have incorporated this into a Neo4j instance. So the knowledge graph, after it's been created, we can look at relationships between the reports and events, and we can maintain this. So an analyst, 1 year looking at, say, the Super Bowl, doesn't have to go back to old reporting to figure out, well, was that a threat at last year's Super Bowl or the last 10 Super Bowls? They'll be able to just connect that type of information or the regional threats and really use that knowledge graph to tie together the information in such a way that it's natural to find similar types of events or actors over time. So we really are helping out the analysts have more operational efficiency in the work that they do. Their time is extremely valuable. They're solving a very important problem that affects everyone in this nation. And we're really trying to do everything we can with graphs to assist them. We also want to move from forensic analysis. Okay, sure, once something bad happens, everyone says, oh, I see it in the data. Forensic analysis, I can tell the news, and I can trace back and say, yeah, you should have caught this, you should have caught that, you should have caught that. That's a much easier problem to do forensic analysis of a known event rather than predictive analysis of events that have not happened yet. You have to be correct every single time and be able to tell the future for things you may not have seen before, people you may not have come in contact with before, different types of threats you haven't experienced before. And that's what makes this a really challenging space to be in. And we've been using graphs in this space for many, many years to more rapidly tie different data sets together and be able to write the graph algorithms to answer those questions as rapidly as possible. So the data sources that we use for the Homeland Security knowledge graph really come from 3 different data sets. The first is a collection of report that's provided by partners. That's a couple dozen reports. And then we use some open data sets. The University of Maryland has a center called START with a global terrorism database. This goes back decades with a database and schema that's very well defined of different events. There's tens of thousands of events in that database. And there's also a list, basically a spreadsheet, with about 211 known homegrown violent extremists coming from research out of University of Nebraska, Omaha, where they've gone through newspaper reports and other information to find homegrown extremists in the US, and it has whether or not they were, what they did, whether or not they were captured, what type of attack they had, are they alive, dead, what is known about them. And so we decided that we would ingest this as, for instance, unstructured text. We would turn this into a graph with vertices, and the vertices we decided would be different media, events, groups, individuals, locations, and then properties of the types of attacks and threats were given as an attack type, for instance, explosive devices, vehicle attacks, et cetera. And then whenever we had a report that connected, say, an individual or a group with a different type of attack, we would place edges into that graph. And what we got was a lot of different pieces. For instance, from Wikipedia, here's an entry. On November 28th, 2016, a terrorist vehicle ramming and stabbing attack occurred at 9:52 a.m. Eastern Standard Time at Ohio State University's Watts Hall in Columbus, Ohio. The attacker, Somali refugee Abdul Razak Ali Artan, was shot and killed by the first responding OSU police officer, and 13 people were hospitalized for injuries. So what we do is we take text, unstructured text, and we create graph objects from it. For instance, they're colored differently to represent the different types of vertices. So we have a person, the attacker. We have two different attack types, a vehicle attack and an edge weapon, a location, Ohio State University. And this is what we start to do to put this information together. We build this graph. And from the threat assessment reports that we had, we initially built a graph here with 114 vertices, 163 edges. Not very big, but some very, very valuable information is contained in this graph. And the different colors of the vertices that you can see represent those different vertex types from locations, individuals, groups, et cetera, media, and so on. So we took that as our starting point, and then we worked into that a global terrorism database that has about 120,000 events each as a row, and we looked for the domestic events within that database, approximately 70,000 or so events. We converted from the database schema, we converted it into a CSV file where one row represented an event with many, many features of that event as cells on that row. And with Neo4j, we just loaded in that as our starting point. And we did some pre-processing with Python scripts. So this is an openly available data set, again, available from the Start Center at University of Maryland. Then we looked at our graph schema and ingestion for how do we combine these different data sets that we had. And we came up with a mapping of maybe fields from those original databases or the reports that we looked at into what our graph schema in Neo4j would be. And eventually we built out a graph with about 325,000 vertices and about 2.7 million edges. And again, I mentioned as we have information that ties together the people, places, and things, and the attacks, and so on, we put edges between. We added those edges into that graph. Any questions so far? So from this, we're able to use very simple queries from Neo4j that I've represented on the screen to help analysts. For instance, we may have a query to find all locations associated with individuals or groups that attack with a different attack type or weapon. Here it just says X2 to represent one of those attack types. So very simply, we have our query over here to do that association query, and just a result over here. Here's X2 in Neo4j, and the locations surrounding it that are related to that type of attack. So that's a very simple query, and we've done a bunch of these. Motif finding. For instance, an analyst may ask, find all locations associated with individuals or groups that attack with both X2 and X3. That's like the Wikipedia entry that I had, where there was both a edge weapon attack and a vehicle attack together. And here we can find individuals who are given in this kind of lavender type color up on the screen. Some of these are individuals that are implicated in using both of those attack types. So this is a simple example of motif finding. We have shortest paths between individuals. For instance, find the closest connection path between two individuals. Here it's the query is on the left, and the two individuals are these two ends of this chain where we're trying to find a connection in that data between those individuals. Now before, you would have to page through different reports, notice different identifiers, go through different databases, and a lot of times these connections are missed. But as we move into this graph space, we can readily find these connections that would go undetected or take many, many hours for discovery in the past. Connecting data, for instance, this is where we create edges, say, between two media used by the same group. Here's Neo4j and a query that is able to do that. And we've also run PageRank and other types of importance rankings to vertices in the graph. For instance, find the highest individual scored by PageRank, and here is just a simple output of vertices that are the individuals and what the PageRank is. So this graph is using Gephi, this for visualization. This is just a community detection algorithm called Louvain that's running on the US events, and the colors represent different communities. I have in the middle the vertex importance with eigencentrality and PageRanks of some of the more influential or important actors, if you will, based on these rankings. And if I look at eigencentrality and look at the groups of some of them, the first one isn't known, but I pull out groups, anti-abortion extremists, left-wing militants. Sure, you came to Graph Connect and never thought you'd be talking about this. White extremists, black nationals, Animal Liberation Front. So we're able to figure out in these types of queries some of the groups that are more central or maybe more influential within this data set. So predictive graph analytics is really getting in front of the data and in front of the problem. With many input graphs, the data is only partially available, so we are either streaming in data sets or we have missing information. We would like to have more, but we have to make quick and rapid decisions based on the data that we have. And also, as I mentioned, these graphs are changing over time. They're not fixed graphs. We're always trying to understand what's changing and what's happening. And unimportant vertices in the past may, over time, become highly important, and we would like to be able to find those. So predictive graph analytics is really the technique where we aim to predict what will happen to an analytic when the data gets filled in or inherently changes. So we have an example of running PageRank and having a predictive PageRank where we may use a training model with transfer learning to train on random graphs and then evaluate it or run it on real graphs. And this highlights the process that we take for doing the type of training. We did random walks which have a natural connection to PageRank, and we developed a neural network system that predicts PageRank using these walks. And I have a couple slides about results. I won't spend a lot of time, it's kind of hard to see, but we looked at training the model, for instance, for 30 minutes on 400 random input graphs, and then looking at the error that we get in predicting large PageRank. On the left is an email graph. On the right is a graph that comes from astrophysics. So we look at applying it to real data sets, and also the distributions of the PageRanks that we get here with different cutoff values, et cetera. And what we have as predicted is kind of the orangey color. The real graph results are the bluish color. The details would take a lot longer to explain to you, but the take-home message is that it seems to work reasonably well across a number of data sets to be able to do this type of approach. And we run all of this work trying to get answers rapidly and fast. So the hope is that we can run all these types of graph queries in time on the order of milliseconds to seconds, even for some of the largest graphs in the world. So to conclude, I want to thank a number of people. I have some research scientists, Jason Reedy, Oda Green, who's now at NVIDIA, working on graph software for GPUs, a number of graduate students currently, and a few graduate students. In fact, I see a collaborator in the audience who's CEO of Traverse, where one of my most recent PhD students, Dr. Anita Zaskryshka, has just gone off to work on these types of problems. And a number of other students also who have been working in this graph space. So we're delighted to be here at Neo4j, and I really appreciate your attention on talking with me about predictive analysis from massive knowledge graphs on Neo4j. So thank you very much. And I can take a question or two or meet you afterwards.
On the example you gave for parsing from Wikipedia, what kind of tools
Oh, so parsing from Wikipedia, that was an example just done by hand with graduate students. Thank you.